So as said just before, let's now continue with a practical example of the Legendre transformation. So this is the practical example. So therefore, let the practical example be starting with the function f of x being x squared plus x plus 1, then f prime of x equals 2x plus 1, and f double prime of x equals 2, which is always for all x greater than 0. This means that f is a convex function on the whole domain. And actually this function is plotted here. So the thick blue graph here illustrates the function f of x. And as discussed in the previous part of the video, the Legendre transformation can be graphically illustrated with tangent lines. Therefore, as before, define now tangent lines. So start with h with a subscript -2. -2 represents here the value of p, so to say, or the slope of the function f of x at the given x naught. So this reads now as follows. So h subscript -2 of x is given by f of x naught. X naught is a function of p, and here is evaluated at -2. Plus f prime x naught evaluated at -2 times x minus x naught evaluated at -2. So the same we can do for, let's say, other values for the slope or the value of p, as elaborated in the previous part of the video. So for completeness, write this also here, just copying from above. And let's make another tangent function h subscript 4 of x. And these three functions, they can now also be illustrated in the graph beneath. So the green line here is h subscript -2 of x. The blue line here, or the light blue line, is h subscript 2 of x, and this purple line here is h subscript 4 of x. So this means here the green line, or h subscript -2 of x, touches f of x at the point x naught, where the first derivative of x is -2. For the blue line, the same is true, but the first derivative of f equals 2, and here for this line the first derivative of f equals 4. And as explained in the last video in the Legendre transformation, we have sort of information transfer from the pair x f of x to the pair p f star of p, and graphically we found, or by analysis we found, that f star of p for a given p equals the negative y-intercept of these tangent lines here. So for this purpose, let's observe the y-intercepts of these functions here. So h subscript minus 2 evaluated at point 0. As you see here, look at the green line, is lower than 0. Then h subscript 2 evaluated at the point 0 is bigger than 0. As you see here, look at the light blue line. It hits the y-axis above the 0 point, or the 0 point, and h subscript 4 evaluated at 0 is lower than 0. Look at this purple line here. It crosses the y-axis below the 0 point. But that in turn means that according to our analysis from the previous part of the video, that f star of minus 2 is bigger than 0, then f star of 2 is lower than 0, and f star of 4 is again bigger than 0. So we expect somehow that f star in this domain starts with having positive values. Then in some region here, maybe where the slope decreases, it becomes for some time negative, and f star again is then bigger than 0. So here you see actually a plot of f star. And first we write the definition of f star again. So f star of p equals p times x naught of p minus f of x naught of p. So the question is now, how we have now, with the information from the last slide, we have now some intuitive information of what f star should look like. But in this slide I would like to cover briefly how now to calculate every value of f star for any given p. This can be done for our particular function as follows. So we know that f prime of x naught equals 2x naught plus 1, and as defined or as found in the previous part of the video, this equals to the value of p. But this means then that x naught equals p minus 1 divided by 2. And interestingly, this is x naught of p. So this is the first value that we need here to calculate f star for some arbitrary given p. And since we also know the function f, again f of x naught equals x naught squared plus x naught plus 1, we can calculate x naught from a given p. We can calculate also then f of x naught. So this can be also written as f of x naught, and x naught depends on p. So with this information, actually, we are done. We can calculate the Legendre transform for f, which is f star. And for completing of the last thing I would like to do in this video, let's have a look at this product of f star. So we have transformed this function f of x within the given domain, which covers the real numbers from -4 to 4. So because we have conducted a variable transfer, also so to say, the domain shifts, or here in the graph of the Legendre transformed, we have different values at the x-axis or at the p-axis in this example. So in particular, we start here at the negative side, and this here is the value f prime of -4, and this is evaluated to be -7. And at the positive values, the domain ends here at f prime of 4, which is evaluated to be equal to 9. So first thing to observe, also the values at the p-axis change due to the variable transfer. And now compare our calculated example with more, let's say, the graphical pre-analysis. So we had here the tangent line with the slope of -2. So this should be approximately here. And at this slope has a y-intercept that is negative, but f star is the negative y-intercept of this tangent line. Therefore, f star of -2 has a positive value. So f star of 2 would be here, I think. And f star and the tangent line here corresponding to a slope of 2 has a positive y-intercept, and therefore here the Legendre transform f star takes on a negative value. And here might be the value 4. And now have a look at the tangent having a slope of 4. It has again negative y-intercept, and therefore f star takes on a positive value. So our calculation of f star agrees with our graphical pre-analysis, and that actually was the goal of this practical example, to give let's say, intuitive explanation with a particular example. So I hope you liked the video. If so, please give me a thumbs up, and maybe see each other next time.